Alright, now that we have looked at grouping data, let's move to graphing the data, getting a picture out of the groupings that we have created. Graphs are essential in statistics. You might have guessed that. And they are what we call exploratory devices, in that they allow us to explore the data. Often you can see something about the data in a graph that you wouldn't otherwise see. Okay, we're going to first look at some graphs for quantitative data, and the starting point here is what's called a histogram. And a histogram is effectively a picture or a graph of the frequency or relative frequency distribution that we had talked about before. Classes are on the horizontal axis, while the frequencies are on the vertical axis. Okay, so for the example above, the physics final exam scores, here is the histogram. You can notice, you recall, if you want to look back at the data, in the first class from 30 to 40 there were 3 scores, and so we have a bar here with a height of 3. In the second class, 40 to 50, there was 1 score, so we have a bar of a height of 1, and so forth. Okay, a thing about histograms, what does it do? Well, it allows us to quickly assess where the majority of the observations fall, the location of most of the data. We can see that quickly in a histogram. We can see that, hey, there's a big chunk of grades between 60 and 90, or between 50 and 90. It also, we get a sense of the shape, an idea of the shape of the data. Okay, a shape of the distribution that generated the data. And if you look at this plot here, we have kind of, if you want to kind of force or artificially force a smooth curve to the shape there, the shape looks it reflects the idea that values in the middle are more likely or more frequent than extreme values, very small values or very large values. Okay, and that's pretty typical with grades, but the histogram allows us to see this sort of thing in the data. Alright, by the way, this plot was created using a program called JMP, J-M-P. I will post a tutorial for that later on. Okay, a stem and leaf plot is another kind of plot for quantitative data. It gives you basically the same information as a histogram, but it retains the original data values. Okay, so back to the final exam score data set. If we had exam scores in the 30s up to the 90s, if you recall, the smallest exam score was a 36. And what we're going to do with a stem and leaf plot basically is you have a stem that represents, you have a stem for every class that you want to partition the data according to. And so if we go along with the same class as we had before, we have a stem that represents 30 to 40. Okay, and we had the first data value was a 36, where the smallest data value was a 36. Then we had a 38, then a 39. Okay, so this is the stem 3, and then I've got the leaves here that reflect the other digits for those data points. I also had a 47, and I also had in the class 50 to 60. We had a 50, we had 2 51s. Now notice I'm going to write that twice because I'm interested in counting occurrences of particular values. A 53, 2 55s, a 56, a 57. In the 60s we had 60, 62, 63, 64, 64, 65, 66, 67, 68, and 69. Again, you'll want to look back at that data to to verify that this is how you would create the stem and leaf plot. In the class 70 to 80, if you look through the data, you'll see there's 3 70s. There's a 71, a 75, a 78, and a 79. And the class 80 to 90, there's a 80, 81, 83, 85, 86, 87, 89. And then classes in the class 90 and above, there's a 95, 98, 9 and 2 99s. Okay, so this is the stem and leaf plot for the final exam scores. Now, if you could take your paper, or however you're viewing this, and turn it 90 degrees, you would see that this histogram looks, that this stem and leaf plot looks like a histogram turned on its side. Okay, so if you, that's hard for me to show in this. I can't really rotate this PDF, but if you rotate your head, you can see that. Okay. A couple of things about stem and leaf plots are that if the data set is really large, that the stem and leaf plots it's not really useful. It becomes overwhelming, just like almost like the original data set in terms of the amount of information that's before you. But for small to moderate sized data sets, it can be very telling. It gives you a sense of the shape of the data, and it also allows you to retain the original data, which again the histogram does not. Stem and leaf plots are also awkward with data that has many digits. So for example, if we had data that ranged, from 15 up to 3,500 and with values spread throughout those two numbers, you'd have to decide, well, where do my stems start? Do I have a stem for 1 for values between 10 and 19, then a stem 2 for values between 20 and 29, and do I do that all the way up to 3,500? That would be a crazy big stem and leaf plot. It wouldn't be useful. So you'd have to restructure your stems and your leaves in a special kind of way, and sometimes that can just get really too clunky and not worth it, and just sticking with a histogram of that sort of data is most useful. So to fill in the blank here, a stem and leaf plot is not useful with let's see here. Okay, is not useful with large data sets, nor with data sets that have many digits in it. Another kind of graph we're going to consider for quantitative data is a time series plot. And basically these plots allow us to see changes in a variable over time. Okay, so here's actually some real data. It's actually 2 time series plots. One data, or one variable, is the density or the population size of Didinium, which is at the microscopic level a predator on the prey Paramecium. Okay, and these two form what's called a predator-prey relationship. The Didinium eats on the Paramecium, and so scientists are often interested in the interplay between these two organisms, really in general between predators and prey. But the time series plot allows us to see some cool things between the prey and the predator. If you look here at the prey density, as time goes on, just say right here, we see an increase in the prey density. And then as it increases, the predator density, or the predator population, is going to increase as well. And but it increases kind of at a lagged rate. It falls behind a little bit. And as soon as what happens is the predator population gets so large that there's not enough prey to sustain it, and so well, actually, let me back up. As the predator population increases, they eat up all the prey. The prey fall off and start to die down. Then the predator follows that just later in time. Anyway, so the point here is not really predator-prey relationships. I actually happen to find them very interesting, but the point here is that this is a time series plot. Okay. Moving on from graphs for quantitative data, let's look at graphs for qualitative data. All right. There's many different graphs or plots that can be used for qualitative data. Remember, qualitative data is naturally non-numeric. It's categorical in nature. Here's an example. If we want to focus on this example down here, in Professor Weiss's class, you may want to hit the pause button and kind of read through this, but in his class there, he looks at party affiliations for his 40 students there, okay, and sees that 18 designate themselves as Republican, 13 as Democrat, and 9 as other. Okay, so those are the frequencies. Again, the relative frequency here would be, this would be 13 divided by 40. That would be the 0.325. So 32.5% identify themselves as Democratic. Okay, the variable that's observed on every person here is qualitative. It's not numeric in nature. The response you would get from a person asking them their political affiliation would be one of these three choices, the way it was set up. And the way we can look at this pictorially, a couple of ways, a couple of common ways, is a bar chart. Now, a bar chart is similar to a histogram, but generally a bar chart, the bars don't touch each other. And so this here is the bar chart down here. You can see on the horizontal axis, it gives the classes or the categories for the qualitative variable, and on the vertical axis it gives the relative frequency of those respective categories. So 32.5% were Democratic, 45% were Republican, and so forth. All right, that's called a bar graph, sometimes a bar chart. A pie chart is a disk divided into wedge-shaped pieces that are proportional to their relative frequencies. Okay, so it reflects basically the same information as a bar chart, but you kind of get a relative sense of the frequency of the respective categories. And so the most frequent category was Republican, and the next most frequent was Democrat, and then other was 22.5%. And so this here is our pie chart, and it reflects a similar sort of information, but again, it's relative to the other categories, is what you see with a pie chart. Those are the common graphs for qualitative data that we're going to consider so far. Moving along, graphs, a feature of graphs, usually a feature of quantitative graphs that we're interested in, is their shape, this idea of symmetry and skewness. So that's an important characteristic we want to consider, is the shape of the data. And the shape of the distribution often determines which statistical method we're going to look at. We're going to use to analyze the data. Again, that's in later chapters, but knowing something about the shape of the data is very important in choosing the right kind of method. In addition to looking at the shape, we can concentrate on overall patterns in the data, all right, rather than just minor differences in a few observed values. Sometimes we can use a smooth curve to approximate and identify the overall shape of the distribution. All right, and that's nice if we know something about a shape that approximates a data set's distribution, then we can maybe use that approximate shape to lead us to the appropriate statistical methods. Okay, again, we do this mostly for quantitative data. So common shapes for that we look at here are symmetric, what's called right skewed, and left skewed. Symmetric here, even within symmetric, we're going to break it down into 4 categories. There's bell shaped, And I'm going to draw, instead of a histogram with bars in it, I'm going to kind of draw a smooth curve that would reflect the general shape of such a histogram. Bell-shaped will look something like this. Sometimes it's called mound-shaped. But you can see it's got one mode, one maximum there, and it mirrors about that middle point there. It looks like a bell here. And the thing about a symmetric distribution, it reflects that moderate values are more likely than extreme values. Okay. We could also have a uniform shaped distribution. It might look something like this. Okay, and this kind of reflects that there's bell shape. This is uniform shape. This reflects, you know, that the values in the data set are equally likely. Okay, we have roughly a histogram that would look roughly flat across, would reflect that frequencies are roughly the same across all classes. Triangular, you know, you might see something like this. This is, you know, it's somewhat close to bell shape, but the mode is a little more peaked here. Other plots we could have, we might have something that's symmetric but not bell-shaped. Maybe it's U-shaped, something like this. And so maybe we'd have a plot that would look like this. This would reflect that that moderate values are less likely than extreme values. Okay, and that's because there's more, the bar heights would be higher on the extreme values, the extreme lows, and the extreme highs here. That said, this is more common. This is the bell-shaped and the uniform-shaped distributions are more common for these sorts of symmetric shapes that we see. We could also have a right-skewed distribution, which is a right-skewed shape. Sometimes that's called positively skewed, and the way you think of right skewed, the way I like to think of it is if we start with a symmetric bell-shaped curve and we take the right tail and we start to stretch it out, it would look something like this. It would start to stretch out that right tail and it would decrease, but it would be right skewed. And what that kind of reflects is that there's some extreme values, there's some extreme large values for the data set. There's a fair amount of them. Left skewed, also called negatively skewed. Similar idea, but our skew is going in the other direction. That there's some extreme small values in the data set, and that's reflected with the left tail being that prominent. Okay, so those are just some general shape designations. The last thing within this video here is the idea of a mode. A mode is the most typical value of a data set, and we can think of this in terms of the shape of the distribution. We can think of a distribution being unimodal. That is, it has one mode. We can think of it being bimodal. And we can think of it being multimodal, trimodal, however many modes you want. Unimodal would, you know, we drew a lot of pictures on the previous page of that, but unimodal has one mode, so something like this. Bimodal might look something like this. Okay, these are more common than distributions with data that have several modes, but those are out there. Unimodal is more common in real life. Bimodal, we do see some, but the idea of a mode is something that we want to be aware of. Okay, graphs and charts for qualitative and quantitative variables.